Welcome to the deep dive. Today we're heading somewhere pretty wild. Not the quiet spiral arms of our galaxy, but right into the thick of it. The Galactic Center.
Yeah, it's probably the most extreme neighborhood in the Milky Way. Just think it's got the highest density of molecular gas, dust, everything, all swirling around our supermassive black hole.
So you'd think logically this would be the place for stars to be born, right?
Yeah.
Like a massive star factory running full tilt.
That's exactly the assumption. It seems obvious. It should be cranking out massive stars like crazy.
But, and this is the core of our deep dive today, there's a twist, a big one. Despite having all that raw material, the gas, the dust, everything you need, a new study's found a really surprising slowdown.
A dramatic slowdown, specifically in the formation of massive stars. And when we say massive, we mean the really big ones, more than 8 times the mass of our sun.
The kind of stars that really shape how a galaxy evolves.
Exactly. They're bright, they live fast, die young, super important. But yeah, things are unexpectedly quiet at the core. It's like finding a high-performance engine just idling.
So how do we figure this out? Seeing into the Galactic Center is notoriously difficult, isn't it?
Yeah.
All that gas and dust in the way.
Oh, absolutely. It's like trying to see through incredibly thick fog. Visible light just doesn't make it through. That's where a specific tool became crucial.
And that tool was SOFIA, NASA's Stratospheric Observatory for Infrared Astronomy, the one that flew on a plane.
That's the one. Now retired, sadly, but its data is golden. Flying way up high above almost all the Earth's water vapor, SOFIA could get these incredibly sharp infrared images.
Infrared light can cut through the dust.
Precisely. It lets you peer through that shroud. Without SOFIA's high-resolution infrared capabilities, honestly, seeing these details would have been pretty much impossible.
Okay, so this new study, using that SOFIA data, who was behind it?
It was led by Dr. James DeBeeser from the SETI Institute and Dr. Wangi Lim at IPAC, Caltech. Their findings got published in the Astrophysical Journal.
And they focused on specific areas.
Yeah, 3 main stellar nurseries right near the center: Sagittarius B1, Sagittarius B2, and Sagittarius C, usually just called Sgr B1, B2, and C.
And how close are these nurseries to the actual center, the black hole?
Ridiculously close. Think about 300 light years, give or take. They're orbiting right in the thick of it.
Wow. And just for perspective, our sun is...
Oh, we're way out in the suburbs, about 26,000 light years from the core. So, yeah, we're looking at the downtown chaos from the quiet countryside.
So what did the SOFIA data actually show about the star formation rate in Sgr B1, B2, and C?
It allowed them to really quantify it. And the results confirmed that the rate of new massive star formation there is, and this is the key phrase, significantly lower than average.
Lower than average compared to what?
Compared to regions of similar size, similar density, but located further out from the galactic center. Places maybe closer to our own solar neighborhood even.
So it's definitely underperforming, given the amount of raw material it has.
Massively underperforming. It's interesting, too, because some previous studies were even more pessimistic. Some suggested star formation might be totally shut down, or, quote, maybe no present star formation occurring at all.
A complete stop. That sounds extreme.
It does. But the SOFIA study offers a more nuanced picture. It's not zero. That's important.
Okay, so how does SOFIA clarify that?
Well, because of its high resolution in the infrared, young, massive stars, hidden deep in their dusty cocoons, they shine brightest at these longer infrared wavelengths. SOFIA could actually pick them out.
Ah, so they could finally see the stars that were forming, even through the dust.
Exactly. Dr. DeBeeser and the team managed to identify more than 6 dozen, so over 72, currently forming massive stars within just those 3 regions studied.
So stars are forming, just not as many or perhaps not as big as you'd expect.
Precisely. They had to look really carefully with the right instrument, but they are there. The factory isn't closed, it's just running really inefficiently. Maybe like 5% capacity, even though it's got mountains of raw materials right outside.
Okay, that really sets up the mystery then. We have the fuel, mountains of it, denser than almost anywhere else. Why are the star-making engines sputtering?
Right, that's the million-dollar question. And the answer seems to lie in the extreme environment itself. It's not just a backdrop. It's actively interfering.
Interfering how? What kind of extreme conditions are we talking about?
It's a combination of things, really. First, these nurseries are whipping around the supermassive black hole at incredible speeds. The orbital mechanics are intense.
Okay, high speed. What else?
Then you've got interactions, powerful gravitational tugs from nearby older massive stars, and potentially interactions with other gas and material that's falling towards the black hole. It's a very dynamic, very disruptive place.
So if you're a giant cloud of gas trying to gently collapse under your own gravity to form a star, all that external pulling and shearing makes it difficult.
Extremely difficult. Stability is key for star formation. A gas cloud needs to kind of hold itself together long enough for gravity to win out and trigger that collapse.
But these external forces, the fast orbit, the pulls from other stars, they're ripping the clouds apart.
That seems to be the main mechanism. They create powerful tidal forces, shear forces, that basically shred the edges of the gas clouds. It prevents the material from clumping together effectively and reaching the critical density needed to ignite star formation.
You lose the gas faster than it can gather in the center.
You got it.
Yeah.
The environment is just too chaotic, too much turbulence, too much external force.
It's like trying to build a sandcastle during a hurricane.
Yeah, that's a pretty good analogy. You have plenty of sand, but the conditions just won't let you build anything substantial.
And does this chaos just affect current star formation, or does it have longer-term implications for these regions?
That's another key point from this study. It suggests a sustainability problem. Because the gas is constantly being disrupted and maybe even stripped away, these nurseries, Sgr B1 and C especially, might not actually hold on to enough material to keep forming stars over long periods.
Unlike nurseries out here in the calmer parts of the galaxy, which can cycle through generations of stars.
Exactly. Out here, things are calmer, clouds can collapse, form stars, the stars enrich the gas, new clouds form. It's a cycle.
Right.
But near the center, the thinking is these regions might only manage to squeeze out maybe one generation of stars before their fuel is just gone, dispersed by the harsh environment.
So fewer stars overall. But you also mentioned something about the type of stars being different.
Yes, that's crucial too. It's not just quantity, it's quality, so to speak.
Right.
The study found that the stars that do manage to form in these regions, well, they topped out at a lower stellar mass than you'd expect.
Meaning they aren't forming the really huge monster stars, even though they have all that dense gas available.
Right. You'd think the densest gas clouds in the galaxy would make the absolute biggest stars. But it seems the environmental stress prevents that. They form fewer stars, and the stars they do form aren't quite as massive as their counterparts in calmer regions.
So the environment forces them to be less ambitious in their star making.
Yeah. Dr. Lim put it nicely. He said the most massive stars they found fall short in both size and quantity compared to what you see in similar nurseries elsewhere. The potential is there, but the environment is actively throttling the output.
Okay, so if these regions look like prime star-forming nurseries, these giant clouds of gas, but they're producing fewer and smaller stars than expected, does that mean we need to rethink how we even classify them?
I think that's exactly what the study implies. It challenges our traditional definitions, especially for something called giant HII regions.
Remind us what an HII region is, typically.
Okay, so an HII region is basically a large cloud of ionized hydrogen gas that's been energized, usually by hot, young, massive stars nearby. Giant HII regions are the really big ones, and astronomers have traditionally seen them as the classic signposts of major, ongoing, massive star formation.
The hallmarks of a successful, active stellar nursery, often still embedded in its birth cloud.
Correct. And Sgr B1 and Sgr C, they look the part. They have the appearance.
But they're not delivering the expected result.
Exactly. So the team argues, well, maybe Sgr B1 and Sgr C don't actually fit that classical definition because of the extreme environmental stress. Or maybe they represent a whole new, previously unrecognized category of stellar nursery altogether.
Wow. So the rulebook needs an update for extreme environments. You can't just judge a cloud by its cover anymore.
Pretty much. You have to factor in the local conditions, the stress, the dynamics. It adds a whole new layer to understanding star formation across the galaxy.
Now, was there any region that bucked this trend? An exception?
Yes, Sgr B2. It's the interesting outlier in this story.
How so? Is it forming lots of massive stars?
No, that's the interesting part. Its current rate of massive star formation is also low, similar to B1 and C. But unlike the others, Sgr B2 seems to have held on to its massive reservoir of dense gas and dust.
So the chaos hasn't stripped away its fuel supply, even though it lives in the same rough neighborhood.
Apparently not, or not to the same extent. It still has the raw materials, the potential for a future burst of star formation. A massive star cluster could still emerge from it down the line.
It's like it's dormant but still fueled up, while its neighbors are running on empty.
That's a good way to put it. It suggests that something about Sgr B2 allows it to withstand the environmental pressures better, or maybe it's in a slightly less disruptive spot temporarily. It retains its potential.
That really highlights the difference between these galactic center regions and, as the study put it, the relatively calm backwaters of our galaxy where we live.
Absolutely. On the surface, giant gas cloud look like giant gas cloud. But the outcome, the number and size of stars produced is fundamentally different depending on whether it's downtown or out in the suburbs. Location, 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 even for stars.
Okay, so let's recap this deep dive. We've seen that the heart of our Milky Way, the Galactic Center, which should be this incredibly fertile ground for massive stars.
Is actually surprisingly sluggish. The star factories are running slow, and thanks to the infrared vision of SOFIA, we could finally quantify that.
And the main reason seems to be the extreme environment itself.
Yes, the intense gravity, the high speeds, the tidal forces, they're actively disrupting the gas clouds, making it much harder for them to collapse and form those big stars efficiently. It's physics in action on a galactic scale.
And this finding is actually making astronomers reconsider some basic classifications, like what even constitutes a giant HII region when you're talking about the unique conditions of the galaxy's core.
It forces us to adapt our models. What works out here in the spiral arms doesn't necessarily apply one-to-one in the extreme environment of the center.
So we've learned a lot, but there's still that intriguing puzzle piece, Sgr B2, the one that's holding onto its fuel despite the chaos.
Right, it stands out. While B1 and C seem to be struggling, B2 is still primed for future action.
Which leaves us with a final thought for you, the listener, to ponder. Since Sgr B2 seems to be resisting these powerful disruptive forces better than its neighbors, what's protecting it? Is there some kind of specific shielding mechanism? Maybe its own gravity is just that much stronger? Or is it in a slightly luckier orbit?
Understanding exactly how Sgr B2 manages to hold on to its potential in that environment. Well, figuring that out could be really key to predicting the future story of star formation right in the very heart of the Milky Way. What will the core look like stellar-wise millions or billions of years from now? Sgr B2 might hold some clues.